Okay, so last time we stopped at this point. We said that to model a language using the statistics of word counts is very effective. It's a very simple method, but using simple assumptions, bias theorem, and simple assumption of the Markov independence rule, we can very easily give the answer to questions like what is the probability of having the word after this many words, or what is the probability of a given sentence in Turkish or in English. Okay, that was the thing that we did last time, and actually we kept using bias rule and the chain rule, and to get rid of some complications we did this maybe just pull the curtain down. We did this assumption. We said that we don't have to be dependent on all the previous words to calculate this equation. Maybe we can just assuming a prefix of n words should be possible. That's what we did, and then that made our things a lot easier, and that way we would be able to calculate the probabilities of the complete sentences. Okay. To estimate the very simple probabilities, though, we use the maximum likelihood estimation. That is, count the number of words given in a corpora, and that will give you the prior probabilities. What do I mean by prior probability? When I say, what is the probability of the, okay, it says that, okay, count the occurrences of the word the and divide it by the number of words in your corpora. That will give you the probability of the, but this is maximum likelihood estimation. Okay, that's one way to give a value for this probability p the. Okay, this is not the only way of estimating stuff. This is the maximum likelihood estimation. It works up to some point, but at some positions it has some problems. For example, what is the probability of the word very, okay, I don't know if there exists such a word in English. Yeah, there exists such a word in English. I think it comes from Old English. What is the probability of P in using maximum likelihood estimation? Depends on your corpora. If this word did not happen before, did not see it, so it is going to assign a probability of 0. That doesn't mean that there is no chance that you are not going to see this word, because this word exists in English. It's only a very rarely used word. Okay, so maximum likelihood estimate, that's why is not a very good estimation method to estimate the probabilities for all the words. So we have to do something about this. But for now, we said that let's use this maximum likelihood estimation for assigning these prior probabilities or the conditional probabilities. Then we will look at this small restaurant data set. You remember this one? It says, okay, what is the how many times did you see I want together? Okay, it says I've seen it more than 800 times. How many times did you see, okay, Chinese food together? It is 82 times. So this is good table, okay, binary. This is bigram table, and there is a unigram table. Unigram table is here. I have seen the word Chinese 158 times. I have seen the word food this many times, and etc. Okay. I have never seen the word tail. Okay. What is the? I think it's in Old English. Muscular power or development. Pillar, okay. So beef, brown, mean, muscle, kind of a muscle. So didn't see it much. 15th century. Nobody uses much. That is such a word, okay. So it doesn't happen, of course, in my restaurant data set. That doesn't mean that its probability should be 0. So we are going to look at that problem today. What happens if I did not see that word or that bigram or trigram before? We are going to offer a few alternatives, and as always we will make a discussion about what did we achieve and what is bad and what is wrong about this.
Last time you mentioned the unknown program.
Yeah, we will talk about that too. Well, unknowns are different from rare words, okay? Unknowns are a kind of, I did not see this before. So, I mean, whenever I looked at English, this word is not there before, because every day you keep adding new words to the language, okay? New acronyms, new words, new places, new names, and etc. Those are the unknown words, okay? These are not unknown words, okay? We will see. I mean, I have 40,000 words in the dictionary. They are not unknown, okay? But in our restaurant data set, you don't have to see all of them. Some of them will be missing, okay? That's one thing. That's about the words. Also, for the bigrams, okay? Most of the bigrams, possible bigrams, you will not see because you don't have enough opportunity to observe the whole language, all the sentences. So that will be a problem. Okay, so I am going to skip this part because we already looked at them. And the Shannon methods of producing sentences from our distributions, we looked at them too. And I think we somewhere stopped around here. So how do we know that what we are doing is good? So evaluation, I think what you're talking about this, unknown words.
Yes.
Yeah, so this unknown word is this, okay? A word that we did not see before, the word that does not exist in the dictionary, okay? There are many words. For example, if you look at Merriam-Webster dictionary, okay, I don't think that you are going to see the word Gebze or Darija, okay? It will not be there, okay? So that will be an unknown word for you, because I mean you cannot put those kind of words in a standard dictionary. It will be an unknown word. Probably that Tiu will be in the dictionary, but Darija will not be in the dictionary. Even if it is in the dictionary, Bayramol will not be in the dictionary, right? So those are the unknown words. For the unknown words, you don't do you don't count them as a separate words. What you do is you put these kind of words in a separate class called unknown, okay? You count the number of unknown words, okay? Whenever you see a new unknown word, you get its probability by calculating the probability of this word, okay? So you consider them as a new class of words. So perplexity is the measure, the simplest measure that we are going to use to measure how good our model is for that language. So formula is basically, okay, remember this is our probability estimation. By the way, this should be like this, not like that, okay? So calculate the probability of a given sentence. So this should be as large as possible, so it should be close to 1. Of course, it won't be exactly 1, or very close to 1. So we want this number high. If I divide it by 1, okay, if this number is big, it could be at most as big as 1. Okay, so 1 over something. I want this number to be small than. If this is large, if I divide it by P is going to be small, right? When I take the nth root of this calculation so that I normalize with respect to the number of words. Okay, so it is normalized with respect to the number of words in your sentence. Okay, so that's called the perplexity. So the minimizing the perplexity is the same as maximizing probability. So you want your perplexity to be as small as possible, probably 1. One probability, one perplexity is not achievable for any model, okay? Because none of your sentences will give you a probability of 1. So 1 will not be possible except for the trivial cases. So you want all you want is I want my perplexity to be as small as possible. What kind of values we are talking about? This, for example, Wall Street Journal dataset. Remember our unigram, bigram, and trigram models, language models. Very primitive model, a little bit better, a little bit better. So as you see, trigram perplexity is much smaller than unigram perplexity. So this is a much better model than unigram model. Okay. So most of the time you won't see this kind of differences between the models, because compared to this trigram model, unigram is very primitive. Okay, so perplexity is something that we need to remember when we are measuring the success of our model. Some people say that by running this perplexity experiment on your model is not very healthy. You may adjust your model so that perplexity is coming better and better and better. You should test your model in a real world application, okay? That's called extrinsic evaluation, okay? Put your model in a real application and evaluate. So what kind of model is this? It could be a speech recognizer, or it could be a machine translation system from Turkish to English, and etc. If your model works very well, if it improves the overall results, then you are doing good with your model. That's what we say. For example, I have a system, translation system. Okay, it takes in one English sentence. I love school. Okay. Then this translation system will produce you a Turkish sentence, and there are maybe a number of alternatives, or while I am translating it, I am using the Turkish model, language model, and the English language model. If I am using 1-gram or 2-gram or trigram models, it will give me a result, right? So I am going to measure the success of my translation system using this. This is a score. This is a score to measure the performance of a translation system. If my system is doing fine with my new model, then I say that okay, the only difference between these two translation systems is their language model. This one is doing better, so I can say that in a real world application my model is doing better. So this is called extrinsic evaluation, and I can use a translation system or the speech recognizer or the summarization system, whatever you choose, real world applications again. Extrinsic evaluation is better than intrinsic evaluation, which is the perplexity based. Of course, perplexity is something good. Of course, we should test it, try it, but what matters is the extrinsic evaluation. We don't develop language models just to make language models. We develop them, okay? We develop them to use them in some kind of an application. Use them in an application and see the final results. Okay, it's called, again, extrinsic or in vivo evaluation. It is difficult actually, time consuming. It takes days to run your experiments, okay? If you don't have that kind of time, or if you are doing some very fast development, then you are going to use intrinsic evaluation, which is the measurement of the perplexity. Okay, so good. So let's go back to this zero counts. What did we say? We say that what happens, I know that there is a word in my dictionary, but it didn't happen. The probability of the probability of me seeing that word is zero. No, that's not true. This becomes even more more evident if I look at the bigrams. Okay, remember Shakespeare? Shakespeare produced almost 300,000 bigrams. Okay, out of 844 million possible bigrams. So in English, in his time, this many bigrams are possible, but he used only 300,000 of them. Okay, what does that mean? All the rest are not possible to use. They are not meaningful. Of course not. Okay, Shakespeare didn't live long. Even if he lived long, there is no way that he could have used all possible bigrams. Some of them are not really possible. Some of them are really, really rare. Okay, so almost 99.96 of these possible bigrams were never seen. Okay, had never seen. They are zero entries in the table. Okay, very nice sentence. Does that mean that any sentence that contains one of those bigrams should have a probability of zero? Of course not. Even that bigram did not happen in Shakespeare's data set. We shouldn't estimate their probabilities as zero. That's what we are going to look at. This is a zero count. Okay, so for this again, we are going to use some ideas from the other parts of the science world. Okay, somebody came up with this idea. If you are observing something, this will happen. A small number of events occur with high frequency. It will occur a lot. Okay, so if you ask people how they are feeling, most of them will tell you that they are fine, or maybe they will say that I am feeling a little bit tired. Maybe they will say that that they are feeling a little bit, they have a little bit headache or something like that. So a small number of events. So I am fine, a little bit tired, some headache, like three things happening 99.99% of the people. Okay, so that doesn't mean that there are no other diseases in the people, because there are there is a very large number of diseases and people are having these diseases, but they don't occur very frequently. So a large number of events occur with a low frequency. Okay, so what there is this rare disease of what we call it Akdeniz ateşi. What do you call it? Akdeniz neyi? Anemisi. So it is very rare, but it happens. So the number of people having it is small. Okay, but there is such a disease, and it is with very low frequency. Along with that disease, there are many other diseases. Okay, hundreds of other diseases. Most of them you never heard of. Okay, but they occur. So the Zipf's law says that a small number of events occur with high frequency, but a large number of events occur with low frequency. That's the same thing with the bigrams. Okay. Okay, the man. This bigram happens a lot in any data set. It's a very popular bigram. So there are not many of them like these kind of bigrams, but they occur a lot. Okay, small number of events occur with high frequency, but a large number of events, a large number of bigrams, there are many of them, but they occur in a very low frequency. They are very rarely used. Okay, so we can very quickly collect statistics on the high frequency events like this one, but we may have to wait. We may have to wait arbitrarily long time to get valid statistics on low frequency events. Okay, so what are we going to do? It's a very dangerous thing to say that I did not see this happen before, so the probability of seeing this word or this bigram is zero. is a very dangerous thing. So we should take this into account. So maximum likelihood estimation is not a very good estimation method to measure the probabilities of those kind of cases. So somebody came up with this idea. They said that, okay, let's do this add one smoothing. I am not, maximum likelihood estimate says that the probability of seeing a word is counting that word and dividing it by the number of words. Okay? Laplace estimate says that no, add 1 to all the words counts. Also add this V to all the occurrences of the words. What is V?
The number of the words.
The number of words in your dictionary, right? What is N? N is the number of words in your data set, right? So this is talking about billions. This is talking about thousands. Okay, in Wall Street Journal, I think you have 3 billion words. In English dictionary, you have 40,000 words. Okay, the word to you happened maybe 0 times in my data set, but I am making just one. So you are incrementing all, you are making all the ones to all the zeros to 1, right? So that's what we are doing. So to calculate the probability of a word then is just 1 over this one if it did not happen before. So this is a very simple assumption. It says that if I did not see anything before, that doesn't mean that it won't happen. It's a very small chance that it will happen, but it will happen. Okay, there is a chance. Also, this one calculates the probability. So what did we do? We say that actually our occurrences of those words increase by 1. But what does that mean? I mean, if I have n words, okay, some of the words did not occur at all, but I incremented their counts to 1, so I have to decrement the other words counts a little bit. So I calculate the CI, that's the reconstructed counts. So the words that have occurred only once before, I multiply their occurrences with, okay, 1 plus 1 times n over n plus v. So their counts are a little bit larger or smaller? What does this mean? So CIs become smaller or a little bit smaller, right? Well, actually, a little bit depends on the comparison between this n and v, right? If n is too large, v is small, then a little bit smaller. If n and v are comparable, then a lot smaller. Okay, so these are the reconstructed counts. Sounds like a good idea. So this is a classical example. Again, let's go to our restaurant data set. Remember, I1 had occurred 827 times. Now I increment it by 1, so it is 828 times. All the zeros became 1 now. Okay, all the bigrams that I used to say 0 are now 1. Okay, so if I need to calculate something, I can do that. These are the probabilities. So the probability of given want, what is the given I, what is the probability of want after that? It is 0.2. Okay, given Chinese, what is the probability of want after that? It is very small, but it is not 0. Previously it used to be 0. Okay, so this kind of addresses our problem of zero counts. This is called smoothing. You are smoothing your counts, you are smoothing your probabilities. And Laplace smoothing, or the other name is add one smoothing. Where is that picture? Yeah, okay. It's called add one smoothing. Tries to address this problem by adding 1 to all the counts. After that, the probability number changes and your count changes too. Okay, as always, okay, this is how the counts change. But the thing is this. When I look at this reconstituted or reconstructed counts, Remember this 800 value, 827, something like that. In the reconstruction, it went down to 528. So very large differences. So see this one. Chinese want, it says occur 0.098 times. So these are not integers anymore, obviously. Okay, the occurrences have changed. So it changed a lot. I wonder what this is. What eat food? What was the eat food was 3. Now it became 1. So all the numbers went down because I need to increase these numbers from 0 to 1, right? That's why all the numbers have decreased. But some of them are very to spend. Let's look at this. To spend went from 200 to 130. There was one extreme case. To eat 430. Here it is 600. So it is 50% reduction in these numbers.
Yeah.
So
I want to also drop.
I want what?
Want
to, from 600 to, well, all of them will go down. It's 1/3 of the original count, right? Something is not that right, but I mean, this is kind of an assumption. I mean, I cannot just increase all the numbers by 1. If I do that without decreasing some of the numbers, my probability numbers will not add up to 1.0. I have to do this. Okay, I have to do this. So my probabilities of other counts are going to be affected a lot, and this is going to be creating a number of problems. So big change to the counts. For example, this is not count 2, sorry. This has to be 1, 2. 1, 2 went from 600 to 200. Okay. And the probability, I mean, I don't care about the numbers. All I care about is the probabilities. Given 1, what is the probability of 2? It went from 66% to 66% to 26%. Those are not very good numbers. So it is flawed. It is a little bit not usable by itself, but it's a good, simple approach for addressing the zero count problem. So for pilot studies, okay, and for cases where, I mean, if you have a lot of zeros in your tables, then this is not usable. But if you don't have that many zeros in your table, then this is usable. Tell me why this is usable if you don't have that many zeros. In your table, if you don't have many zeros, then they say that it is usable. But if you have many zeros in your tables, this is not usable. Why?
Because the relative change is not that much.
What did you say?
Relatively speaking, the change wouldn't be that big.
Yeah. What are we doing? We are increasing all those zeros to 1, and we have to discount all the others so that total number of word occurrences will stay the same, right? If you don't have many zeros, then you are not going to add those numbers up to those zeros, and discounts will not be that high. So that's what we are talking about. So Laplace smoothing or advanced smoothing is not used much, but it's a good introduction. So let's look at a little bit better smoothing methods. Okay, good turning. Okay, Turing, Neisser-Knee, Wittenbell. Okay, the same thing. They are all doing the same stuff. Okay. Is to use the count of things that we have seen once to help estimate the count of things that we have never seen. Okay, so if you have observed something just once, that's a very interesting thing, but that thing is very close to the things that we did not observe before. That's the idea. So maybe that sentence did not come out very understandably. So let's look at this example, classical example. So we are fishing. So these are freshwater fish, carp, perch, whitefish, trout, salmon, eel, catfish, and bass. I don't know what they are. I think this one is alabalık. yılan balığı. This is salmon, right?
Salmon.
And this is kaya balığı. These are all freshwater. Tatlı su balıkları bunlar. Yeah, so I know that in my dictionary there are 8 types of fish. Okay, I know that I'm going to get one of them. Okay, if I get something else, that would be an unknown fish, so I am not going to consider it yet. So far I have caught 10 carp, 3 perch, and 2 whitefish, and 1 trout, 1 salmon, 1 eel. Okay, and a total of 18 fish. So I did not catch any of these, or what else? Whitefish is there.
Catfish, eel.
Catfish, I know I caught 1 eel. I got trout. Whitefish is there.
Perch.
We like the caught are 6 types and we have 8 species. So
Yeah, okay, so that's enough. So the question is, how likely is it that the next fish caught is from a new species, or the catfish or bass? Then what am I gonna say? Okay, I mean, maximum likelihood estimation says that you have never caught a catfish before, so you are not going to catch it. That's not true, right? So that's maximum likelihood estimation. That's not true. So, but we say that our chances of catching a new fish, new type of fish, is as much as catching a fish that I have caught on once. So 1 trout, 1 salmon, and 1 eel. So 3/18. So that probability is 3/18. We are talking about fish hocam.
Hocam, online yayın yapabiliyor musun?
With my with my cell phone, yes.
Yes.
So this lecture is costing me 3 kuruş per minute. 1 kuruş.
O kadar değer veriyorsun öğrencilerine.
Yeah. No. I am valuing myself, not them.
Ay, daha See you hocam.
And that's my.
approach. Attitude is right.
So you are costing me like 5, 10 kuruş now. if you can go ahead.
Bende yok hocam. Bozuk taşımıyorum. Kredi kartı.
Put them in the box next to the door. Okay.
Fish.
So catching a new fish, this is the probability. So either this one or that one is 3/18. That's the idea. I am not saying that there is a theory behind it. I am not saying that this is how it should be calculated. Okay, this is just an intuition. There is no theory behind the maximum likelihood estimation either. Maximum likelihood estimation explains your data. It doesn't explain what's going to happen, right? It says this is what happened, okay? And this one says that this is what happened and this is what I'm expecting. Okay, this is the good Turing intuition. So if 3/18 is the probability of I am going to catch a catfish or bass, so then what is the probability of catching a trout then? It should be less than 1/18, right? Because everything has to be at to 1.0. So I have to do some discounts from the trout or the salmon or the eel. Okay? So that's what we are going to do. Let's do that, okay? So, but it looks like I am out of time. It has been 45 minutes. Let's stop here. When we come back, we will do these calculations. I will give you some formulas. Difficult to remember formulas, but things will make sense. Okay, let's be here around 15:01.
hocam yanlış saat yazdınız galiba.
Efendim?
Saati yanlış yazdınız.
Kaç olacak?
Buçuk olmayacak mı?
Yeah.
12 falan işte. Liste böyle oldu.
14:31.
Buradan bunu nasıl çözdüm? Şunu
Okay.
o şekilde.
da bu ödevle alakalı. Ben anlamıştım. Başka dersin üzerine yüklemiş.
Okay.
Ya ben sana cevap yazdım oraya, yazmadın mı?
Yazdınız da hani onu da söylemiyorum. Başka ders.
Tamam, ya bir durum olsa söylediğin gibi böyle olsun diye.
Tamam.
Okay.
Ne var hocam? Nasıl koyma?
Nasıl ya?
Evet. Uzun kısa. Ahmet'e.
Şeyleri uzun
Hı hı.
bıraktı ya.
Bak şunu yapması çok kolay. Bunu hemen anlıyorum.
Ben de
SOS tamam mı? Bu artık beynimize hardcore bir şekilde bak.
Bıraktım, tamam.
bırakırsın geldi.
Ama ne zaman başka bir şey geçsek takip edelim. Kardeşim hazır mısın? Ya bir de bizde de şey hani ABC'de diye gidiyor. Arap şeyi yok böyle noktaları ayrı, uzunları ayrı diye başlatsa takip etmesi daha kolay olacak da.
Hani bir de yani mesela diyelim ki başladın.
Hadi bakalım. Hadi bir şey yolda sonra.
Durakları da anlamaz.
Onu şey yapıyoruz, bekliyoruz onu.
Kağıtı ver. Kağıtı verir misin?
Tamam hadi. Hazır mısın?
Hazırım.
Adam geliyor.
Dur.
Bir daha yapayım mı?
Hayır.
Tamam.
Ben bu telefonu yanıma alabilirim değil mi? Ondan sonra devam ediyor.
Bu kadar.
Bende dur. Ve tamam.
Okay. Fatih mi gönderdi? Bana Fatih İ harfi gönderdi.
Fatih değil mi? Kanka şey.
Ha, T o uzun o. D.
Fatih oldu sen o zaman. Başlayalım.
Bak genel olarak işte onun bir akışı var. Dur. Akışı bu şekilde işte. Harflerin arasında yani şu vuruşların arasında bir belli aralık olması, harflerin arasında daha geniş bir aralık, kelimelerin arasında daha geniş olur.
Hadi.
Peki. Dur. Okay.
Hı hı. Tamam, şimdi tamam bakıyorum kardeşim. Sen bana demiştin ki
Sonra ne çıktı?
Sonra şey yapacağız. Minimum edit listesi yaparak ne söylediğini bulmaya çalışacağım bekleyeceğim. Lüks mü? Şimdi Morse kod üzerinden
Bunlardan sence 3 harf doğru.
kardeşim biz bu işi boş yapıyoruz ya.
Peki. Eğer kalemde değil ile gidersin. dur. Bir,
Tamam.
sen bana bir şey göndereceksin. Haydi gönder.
Bip bip. Bip bip. Bip bip.
Bu kadar.
Bu kadar.
Ama mı?
Evet.
Okay. Alright. Beep beep.
Tamam.
Beep
Dene.
beep beep beep beep.
Tamam.
Beep beep beep beep.
Tamam.
Beep beep beep.
Tamam.
Beep beep.
Bu kadar.
Beep beep. Beep
Dur.
beep.
Bip bip.
Beep beep beep beep.
Hı hı.
Beep beep.
Sondaki iyi. Bak bu kadar öğrendik.
Beep beep beep. Hasan hala çıkarmadın sandın sen çıkartıyorsun onları.
Şimdi baştaki ne? Na. Kısa, uzun kısa. Nap. Uzun, kısa, uzun. Ye, o, ne, ne mi? Bak, kısa, kısa, aha, ne yapıyorsun?
Sakin ol.
Uzun, kısa. Sanırım ben şuradaki kısmını en sondakini yanlış yapmışım. Tamam güzel. Evet. Kardeşim mesajını aldım. Çok güzel bir mesaj. Mind. Dur. Kısa ve etkili bir mesaj göndermek lazım.
Vay canına.
Bip bip bip. Bip bip bip. Bip bip bip. Bip bip. Bip bip. Bip bip bip. Bip bip. Bip bip bip. Hemen sana yazdıktan sonra şeyini şey yap. küçük susamaya demiş. Yeter bu kadar.
Bu kadar. Ben bir crash da hissettim. Araba öyle. Bu ne?
Şeyden geri kalanlar. Biliyorsun olacak.
Abi boş mu? Bakabilir miyim?
Bence boş değil. İçinde bir şeyler var.
Ne içinde var?
Yok. Belli.
Öğrendiniz mi? Cuma
Yaptık.
Bir şeyler yapabildik.
Yani receive data olayını hallettik. Böyle şarkı şarkı.
Sen anlatabilir misin?
Saniyede 2 harfle. Ya bana yaklaşık 3 kuruşa falan var diyordum. Bana göre.
İşte ortak. Ödevi ben yanlışlıkla yüklemişim. Başka dersini de. Geçen makaleleri yüklerken fark ettim. Sonra hocaya mail attım böyle. Hoca tamam dedi, hatırlatırsan dedi yaparız dedi. Ödevleri okurum dedi ona.
Mail atsaydın.
Mail attım aynen.
Ama ödev geç yüklenebiliyordu galiba da.
Ama puanım kırılacak yani bayağı bir.
Ben de paper'ı yüklerken geç yükledim. Sonra kapandı. Yükleyemedim. Hocaya mail attım ama bilmiyorum kabul eder mi?
Eder ya, şu an çok sıkıntı değil.
Bence ama orada kapandı yani ama ödev kapanmıyordu.
Ona demek ki değil, submission koymadı demek ki paper'ları.
Koymamış.
Eder ya, sıkıntı. Puan vermeyecek zaten onlara.
Evet.
Sadece hani bizi biraz daha yapmak için.
Süreye uymak için.
Bulabildin mi paper?
Yazdım ama şimdi sordu. Sonra işte değiştireyim diye biraz daha yapayım dedim. Sonra daha bakmaya böyle bayağı
Nereden buldun? Hangi derdi?
Valla skorlardan baktım ben ya.
Yani hangi derdi, hangi veya bir konferans makalesi falan mı?
Valla şu an hatırlayamadım ya. Arşiv miydi acaba? O kadar çok paper baktım ki. En son arşivdi herhalde.
Ya olunca, bir yeni olunca NLP falan konularda
Evet,
bu makale bulması biraz daha zor olur.
İçeriklerine baktım biraz zor geldi anlayamadım ama nasıl anlatacağım bilmiyorum.
Task yani ne üzerine?
Önce dersten attığımız ya test diye bir şey. Onun üstünden devam ediyorum. Bir o gösterdiği paper'la onun bir tane kullanıldığı referans verdiğini seçtim. Bir konteks diye bir şey diyor. Ne olduğunu tam bilmiyorum. Sen seçtin nasıl?
Ya benimki bu sentiment classification var ya, duygu durum analizi. Onu yapmışlar, cross domain yani bir tane başka bir diyelim atıyorum. Amazon'daki aldığı, Review'lardan aldığı data seti başka bir yerde kullanmışlar, başka bir yerde.
Onları da gördüm ama baktılar biraz zor geldi bana.
Ama benimki de zor ya, şeyden gelmiş. Transaction falan. Yani alternatif transaction şeysi var. O transaction'la başlayan şeyler derdi. Yani kaliteli daha yani şeyleri yüksek. O yüzden
Benimkilerine de bakmışlar. Şimdi çoktu ama hani çoğu yönde referans verilmiş makalede.
Okay, we are back. So, for this we are going to define this function nx. What is the meaning of nx? Nx is the frequency x. So it sounds complicated, but it's not actually. Frequency of n10 means how many of the fish types did you catch 10 times? So I have only caught carp 10 times, so just one fish type, and 10 is 1. And 1 is 3 because trout, salmon, and eel are just the 3 different fish types that I caught only once. Okay, so n10 and n1. So nx is the frequency of frequency x. So it looks like n10 is 1, n3 is 1, n2 is 1, okay, n1 is 3, and n0 is 2, right? This one, then this one. Okay. So to estimate the total number of unseen species, then we do this, okay? We use C star means that it is the reconstructed or recounted numbers. C star 0 is C1. Okay, so I am going to accept that. See, what is the, again, N0? N0 is the number of fish types that I didn't catch before. So it says that count C0 as C1, and P0 is going to be N1 over N. Okay, for all the rest of the C's, this is what I do. You add 1 to it, and you calculate, you use the one level up count and divide it by NC. So it looks like all the counts. So what is this? Do you think that this will be high? Well, it depends on the actually fish type or the number of fishes that you caught. But it looks like most of them will be counted a little bit less than the original one. But the effect that we are going to get will not be as severe as the advanced smoothing that we get from the Laplace smoothing. So these are all the adjustments. Let's look at this one again. So GT means good tuning. Okay. P star GT is for the of course things with frequency 0 in the training, and 1 over n. Okay. And if I like to do it for the eel is caught once, right? Yeah, it is once. So its probability is going to be, okay, the P eel is going to be, count of eel is going to be 1 plus 1 times 1 over 3. That means, okay, 1 is the number of counts. 1 is this one, okay. This is 1 plus 1. NC is 3 because 3 different fish types are caught only once, and NC plus 1 is 1, so it is 2 over 3. So this is not actually true. This is not P eel, okay. This is C star 1. So don't see this one, okay. This isn't true. Okay, I got these slides from Juravsky's site, and he got these slides from Josh Goodman. I don't know where he got it, so somebody made a mistake. It's not me. I just copy pasted it. Or no, I'm just using the PowerPoints, and that's it. So instead of, remember, the count of eel was 1. Now it is 2 over 3. 2 over 3. Okay. So let's try to compare this with the maximum likelihood estimation. So previously, unseen fish, just these two, it used to be 0, okay, and our maximum likelihood estimation say that if you didn't catch before, you are not going to catch it. It is 0. But with the good tuning intuition, that number becomes 0.17. So there is a 17 percent chance that you are going to catch an unseen fish. Okay. For the trout, I caught it only once previously. Okay, I caught it only once previously. And maximum likelihood estimation says that you have a chance of 1 over 18, okay, catching a trout again. But C star says that no, you did not catch it once, you catch it 0.67 times. It is smaller than 1, and your chances of getting a knee trout again is 1 over 27. Okay, it's not 1 over 18, but 1 over 27. So it is smaller. So this one is not catching catfish or bass, okay? This one is catching an unseen fish. Okay, you have a question? Yeah.
But how can catching an unseen fish be much higher than catching a fish that we have seen?
So what do you think?
Like this
Wait,
model
wait.
should not be, like, in my opinion, it shouldn't be that much valid. Or
How
we
many
have got
types
some-
of fish did we not catch? 2, right?
2.
So trout is just a single type of fish.
Even if we multiply that by 2.
It is 3 over 18, and it is this one and this one, right?
Yeah.
1 over 20, yeah. Well, that's, I am not saying that there is a theoretical justification for this one, but it is what it is, okay?
Seems
So
much-
why do you
much
think that,
problem.
why do you think that,
Anything unseen.
why do you think that we caught a trout before and we didn't caught a catfish, right? Well, it's just coincidence. I mean, we assume that catching one of those fish is the same probability. So if I caught a catfish before, then probability of catching a trout, or if I caught a trout before, probability of catching a catfish is higher than trout. Okay, by the way, you need to divide this number by 2, because I have 2 classes here, right?
Okay.
So if you divide it, it's going to be what? Like
0.85.
18, right? If I divide it by 2, so it will be like
0.85.
what?
0.85 per
0.
No, I am trying to kind of compare these 2 numbers. Okay. I am going to okay. So if you are doing this multiplied by 2, so it is 3 over 36, and compared to 1 over 27, this one is still higher, like larger. And well, we didn't catch any catfish before. Probability of catching a catfish and trout should not be that much different. So the probability of actually catching a catfish should be higher, because I'm expecting their probabilities to be similar. That's the intuition. Again, I mean, the job of maximum likelihood estimation is a very good question, actually. I mean, the job of maximum likelihood estimation is to explain your data that already had happened, okay? It is easy to talk about the things that had happened. It's like commenting on a soccer game that happened before. I mean, these guys won because they had the better goalkeeper, they had the better something. These are just talk, and we are trying to explain something. MLE is kind of doing the same thing. This one is trying to guess into the future and say that this one did not happen before doesn't mean that it's not going to happen. And it will happen, and actually I am expecting that. Catching a catfish or bass is, the probability of it is higher than catching a trout at this case. If you continue this and if you keep getting more and more trouts, of course this picture will change.
We said we got 1,000 fish, and from them 5 trouts.
Yeah, well, I mean, in that case, of course, the probability of trout will be different. It's not going to be like this, right? Because it's nx will be n5 now. We are not talking about the n1 anymore, okay? And the calculation of n1 is different. Where is my calculation for n? Where is my n? Yeah, where is my n? Well, I don't have it. Well, calculation of n new n1 will compare it with the n6 group. Okay. So I mean, I don't have a good answer to your question, or to your comment. But I mean, again, this is just a heuristic, okay? We don't want to see those zero counts. The first stupid way of doing this solution is add 1 to everybody. That was stupid, and that caused some stupid mistakes at the tables. So this is the a little bit less stupid solution, still a stupid solution. Okay. So let's look at this example, and maybe this will explain it a little bit more. AP Newswire, very large corpora with 74 billion words in it. Berkeley Restaurant has 2 million words in it. Okay. Okay, these are the bigram frequencies, by the way. I'm sorry, I mean, these are bigrams, okay? So there are a total of 2 million bigrams available for the Berkeley. Okay, actually it is more than B2, okay, about 2 million and total of whatever, I mean, it is like maybe 2.1 million, and this guy is 70, total of 75 billion. Okay, out of all those 75 billion, 74.6 billion of them did not occur at all. Okay, and the good Turing intuition says that probability that that I am going to see an unseen bigram is this small. Okay, but this one says that probability of seeing an unseen bigram is this small. So if you compare these two, they are very, very different. This one is much higher. Why? Because we have a much smaller corpora than the AP Newswire. Okay, so see this number and this number. You are saying that these two numbers are too close in our previous case. In fact, the second one was smaller than the first one. That's what you were saying. Because we had very small amount of data. And the nice thing about this one is it changes dynamically depending on your data size. And let's look at these calculations again. So this one says that, by the way, these are not probability, these are the counts, okay? Previously, I used to say this bigram happened only once. Now I am saying that this happened 0.44 times. This one happened 0.533 times, okay? So 6 times happened, it is 5. 6 times happened, it is 4.5. So it changes a lot actually. For the zeros and ones, these are smaller. And then afterwards, after 4, I am getting more confident. Look at this one. 4 has increased, right?
Yeah.
Why do you think? It used to be 4, now it is 4.0608, sorry.
Maybe it is a typo.
No,
Maybe it is 3.08.
no. Look at these numbers. Okay. It's going down. Okay. It is not going down fast enough, I guess, in here. It is looking at the one that is C plus 1. And this one is not going down as fast as C. Drop is almost half. Drop is not that much. So it is saying that whatever happened like 4 times, it could have been 5 times or 3 times, right? Something like that. Again, it's an intuition thing, and experimental evidence says that this GT works better than the Laplace promoting. Okay. There are many other complications. For example, is there any Is there any justification for calculating this N20 again? What does N20 mean? The words that happen 20 times? Well, we have enough evidence about this word, right? Maybe I should not adjust the frequency of these words anymore, right? Because it already happened 20 times. Why should I play with the frequencies of these kind of words? Okay, maybe I should play only the frequencies of the words that did not happen before, or just once, twice, 3 times, 4 times, less than 10 times maybe. After that, let's use them as it is. For that one, they have developed this kind of stuff. So for the values of between 1 and some k, maybe 10, use this formula for the recounting. For the other ones, use whatever you had before. Okay, so these are some complications. Formulas are getting more complex, and if you look at the numbers, they will change, and some of them you will have difficulty explaining it, but at the end, we know that if I add up all these numbers, and if I add up all these numbers, they will be the same. Okay, they will be the number of words. They will be the number of words happen in the Berkeley restaurant data set and the AP Newswire data set. I'm sorry, I keep saying number of words. It's a number of bigrams. Okay, so total number of bigrams will stay the same, whatever the calculations we did. Good. Okay. So any questions? Any questions? So far we talked about the words and the bigrams only. Okay. But usually we don't work with the bigrams. We work with trigrams and fourgrams and fivegrams in some cases. Okay. Let's try to see some of the things that we are working with those kind of cases. Back off and interpolation. Okay. Somebody came with this idea. Say that, okay. To calculate this, we need trigrams. Remember this? How do you calculate this one? You would say probability of xy and probability of xyz, right? So I need to calculate this trigram to calculate this one. If I don't have the trigram, they say that if you cannot calculate this one because this is 0 or that is 0, then calculate this one. And if you cannot calculate this one, then calculate this one. Okay? So this is called back off. This is called back off. Why? Because calculating this one is very easy compared to this one, of course. And if this one is not available, then this one is as simple as counting the number of words. Okay? This one is as simple as counting the number of words. And that's it. So that's called the back off. But some people say that let's not do the backing off thing. Let's try to combine these three. Okay, that's called the interpolation. Okay, back off is trigram if you have it, otherwise bigram, otherwise unigram. Interpolation is mix all three, and this is what they say. Okay, to calculate this probability. Okay, calculate this probability really. Okay, and multiply it with this lambda 1 and calculate this one, multiply it with lambda 2 and lambda 3. Of course, these three should add up to, okay, the summation of all the lambdas should be total of 1.0. Otherwise, my probabilities will be messed up. Okay, so where does the lambdas come from? Okay, you calculate them from your training set to make all of your perplexity calculations a little bit better. Okay, or run them in an experiment, and it will make the things a little bit better. And sometimes people say that these lambdas should depend on the words themselves. You understand this one, right? I mean, I have 3 constants for the whole data set here. They say that no, this is not a very good idea. I mean, why should I use the same lambda for all the words? There are some trigrams that I trust them. Okay, there are some trigrams that I trust them because that will happen very often, and if they happen, I will take them. In that case, my lambda 1 will be 1.0, this one will be 0, then this one will be 0. Okay, that's what they are saying here. So if you have seen these words, these lambdas will depend on those trigrams.
So is lambda like weight or?
Yeah, weight.
For the, okay.
Weight, and they should add up to, yeah, it's here. They should add up to 1, otherwise my probabilities will be messed up. Okay, and remember, these lambdas are the same lambdas. They depend on the same number of words. Okay, n minus 2, n minus 1, 2 words. If you have seen these 2 words, these 2, okay, these 2, then use this lambda. So how do you calculate those lambdas again? If these are very frequent words, then those lambdas should be high, otherwise low. Maybe the number of occurrences of those words. But setting the lambdas is another issue here. So how do you set the lambdas? Maybe we should learn to set the lambdas using a held out. What is held out set? Held out set is a portion of your training set which is not used for the training for calculating the probability values. So development corpus, okay, run your experiment on that one. Okay, whatever gives you the best perplexity results or the extrinsic evaluation results, use those lambdas. That's one idea. Other types of backoff strategies, like what is the backoff again? Use trigram. If it doesn't happen, use a bigram or a unigram. There are many ways of doing this. This cat's backoff, I will not talk about it. I don't have time. This is getting a little bit more and more detailed, so I'm going to skip it. And y discounts p star and alpha. Again, I mean, in MLE, maximum likelihood estimation, it is designed in a way that all the probabilities add up to 1. There is no problem with that. But with the new type of discounting techniques, smoothing techniques, you have to be very careful about that. That's why we have those discounts and the alpha probabilities. And finally, this is what I get from the GT smoothed bigram probabilities. Okay. I want is high probability again. Those zero probabilities became the same thing again. These 0 probabilities are different. So what was surprising, to eat, it is this much. Okay. So we talked about this. Out of vocabulary words, again, we talk about this, or unknown words. Unknown words are very different from the words that you did not see before. Okay, for the out of probability words or the unknown words, we don't use GT smoothing or any type of smoothing. Why? Because those words are in my dictionary. I know that they are there. I know them, but they did not happen before. Unknown words are the words that are not in my dictionary. I never seen them before. That's why the algorithm that I gave you before is still valid. Out of vocabulary words. Okay, good. One thing that happens a lot, and this will happen in your homework too, these chain rules, remember the chain rule? It has this large pi probabilities of things. You need to multiply lots of numbers between 0 and 1, right? These are my numbers. If you multiply many numbers between 0 and 1, every time you do this multiplication, the number will get smaller and smaller and smaller. It will get very close to 0. If you are multiplying two numbers like 10 to the power minus 20 and 10 to the power minus 22, etc., these numbers will get larger, so minus 23, 24, and after a while you are dealing with very small numbers and you are going to cause underflow. Not overflow, but underflow, if you keep multiplying those numbers. So that's not a good thing. We don't want this to happen. So what we do is this. We say that if I have a number, okay, if I have a number alpha and beta, you just take the logarithm of it, okay, just take the logarithm of it. Just to keep the number the same, I just take this one. E to the power, okay, or maybe natural logarithm, ln of it. E to the power ln alpha times beta is the same as alpha times beta. But the nice thing is this, I can write the same formula like ln alpha plus ln beta, right? So what I'm saying here is that don't multiply these two numbers and take the ln and this. Get the logarithm of this number, get this logarithm of this number and add them together, then take the exponential like that. So in this way you are not multiplying very small numbers, you are just adding small numbers. By adding small numbers you don't get smaller. Okay, of course everything is above zero. By adding small numbers you don't get close to zero, you get close to 1.0, right? So that's a thing. So take the logarithms of those probabilities and add them, and finally take the e to the power that number. Since most of the time we are comparing numbers with the other numbers, okay, we are comparing numbers with the other numbers, we don't have to calculate this exponential. We just get this number and compare it with the other numbers that we get from the other probability calculations. And the important thing here is the comparison, which one is larger or smaller. We are not interested in the exact number itself. Okay? So this is, I mean, there's a numerical issue, practical numerical issue. Always try to implement your probability calculations this way. Any questions? Google in 2006 they say that, okay, I have scanned all the documents in this world, English documents, and I have all the data on my drives, and I have calculated 1 gram, 2 gram, 3 gram, 4 gram, and 5 grams of English, okay, and I am making this available. If you like, you can download it, and you can use it for anything R&D related. For example, for the statistical machine translation, speech recognition, spelling correction. It is okay for you. This guy, Peter Norvig, is a very famous artificial intelligence scientist, and he was the head of the Google AI. I think he retired. I don't know what happened to him. But important name, his website is still up. He's still making contributions. So they say that they have this many words. I don't know that what kind of number is that. Okay. And they have 5 grams up to 5 grams, and they did not count anything in if it did not happen at least 40 times. Okay. If they have seen a 5 gram that did not happen at least 40 times, they did not include it. They consider it as zero. Okay? And there are a total of 13 million unique words. Okay? After discarding words that appear less than 200 times. So they need to have that word appearing at least 200 times. Very strong statistical thresholds these are. Okay, and if you like to see, so this 4 gram happened 92 times, serve as the incoming. Okay, and this one has happened 111 times, serve as the indispensable. Okay, this is that was what's happening, and there are 5 gram versions of this, of course. So this shows that is a very strong, again, data set. But whatever it is, If something did not happen in the Google dataset, that doesn't mean that it's not going to happen. Okay? And if your application is on a very, very specific field, for example, if you are looking at the biological text, biological scientific papers, then probably your language model should use something else other than the Google dataset. Okay? Google is Google, and Associated Press dataset is Associated Press dataset. They are different. They don't have to explain your data in your hand, so you have to be careful. Google corpus is fine if your application deals with arbitrary English text on the web. If you are dealing with a very formal English, then this may not model your data very well. Okay, good. So I guess that's the end of the language model using statistics and the n-grams. If you have any questions, I can answer them. Otherwise, I will start a kind of related topic, a topic that we visited before, but it was kind of not finished. Now we have tools to understand the rest. I'll talk about it. Any questions? Again, very small mathematics. Very small mathematics. All I did is this. Okay, Bayes theorem. And the chain rule. Chain rule comes from this one. And the Markov assumption. That's it.
Can we use Google Ngrams for commercial applications?
I did not read the. I think it made it available for the commercials too. Because the idea of Google is, if you depend on me, if you are using my data, you are going to give me more data. So that's a good thing. So Google is a data company, right? They made their money by invading our privacy. Okay. So let's start talking about this spelling stuff. Didn't we talk about spelling before? Yeah, spell checking. Well, in that case, what we did was, okay, if I write alt, okay, what is the distance to this word kalb? Okay, so we measured the edit distance between words. I mean, we said that this could be used in spell checking and etc., but we didn't look at the whole spelling correction application yet. And I wanted to delay this discussion until I talk about these n-grams and the language models, because the real spelling correction application needs some kind of a language model. Now we can talk about it. So this is going to talk a little bit about minimum edit distance and etc., but okay, we already know that. Okay, so spelling correction happens a lot when you are typing something. Okay, you always need help from the computer to correct those misspelled words, and we are going to look at this problem. Okay, spelling error detection and correction. One is detection, the other one is correction. Okay, for the correction, sometimes it is auto-corrected. People like it, I don't like it. And it suggests a correction or gives a suggestion list, and we are going to look at them one by one. Okay, types of spelling errors. This is the one, the most trivial. Non-word errors. If you write this one, there is no such word in English. Okay, you don't see this in the dictionary. This is not a new inflectional derivation of another word. So it is a non-word error. So this is the simplest one. Just look it up. If it is not in the dictionary, try to change it to the correct one. The tough ones are this one, real word errors. Instead of writing 3, I write there. Okay, that's a tough one, because there is no spelling error there, right? There is no spelling error. It is just It is just using a different word both of them are spelled correctly. And there are cognitive errors. I want to say peace, but I write peace. Okay, those are homophones. They are read exactly the same. The pronunciations are the same. Peace and peace, two and two, right? They are pronounced the same way. So, but I like to be able to find. I mean, if somebody says, I have seen 3 men, but instead of 3 I write there. I have seen there man. I mean, your word processor should notice this and should kind of suggest that, are you sure about that or this or something like that. Nowadays, Word is doing a very fine job of saying this kind of stuff, right? If the does it fix this one? Do I have spell checker?
You don't.
What?
Apparently you don't.
It's not open, I guess.
Save it as an English file. What did you say?
It is not open, I guess.
Where is it?
On
Is it in the
the
tool?
bottom right, you are selecting TR, Turkish. Bottom, left, sorry, bottom left.
Can I change it here?
You should be.
Yeah, okay. English like that. But even if that one,
Do Control A and change it then.
okay, maybe like that. Okay, tools, review, and it's language, my set proofing language, yeah. English, take automatic. I didn't find it. I was trying to set, I have seen their man, 3 instead of 3 man. I have seen their man, but it didn't happen. But it is, I know that it works. Okay, sometimes it gives you these kind of suggestions. So we are going to look at these problems. Spellings happen a lot. Okay, it says that 26% of the web queries are all misspelled. Okay, when you type something, you always get, did you mean this, right? Even if you write something correctly, you get again the same thing, did you mean that or this, okay? Non-word spelling errors is again, it is easy to deal with. You understand that it's a spelling word. All after that, all you need to do is just give the user a number of alternatives to change it to. Okay, any word in the dictionary is an error. Okay, generate candidates. How do I generate the candidates? Shortest weighted edit distance. So that's what I do. If somebody had written this, okay, if somebody had written this, then I scan the whole English dictionary to find the closest word in terms of edit distance, and I say that, okay, these are one step edit distances to you. Which one do you want to change it to? Okay.
But isn't that extremely inefficient?
Well, actually, our computers are very sensitive. Why? I mean, you have to look this up in the dictionary, right?
Okay.
So that's one search. Maybe you can look it up using a hashing method or something like that, right? So hashing method will speed this up. By looking at, but you could use the same hashing method to find the words that differ only with one or 2 or 3 characters. Okay, so among all of them, find the closest ones. Okay, I mean, you are the engineers. I don't know. I am an NLP guy here. Find a solution. Don't make me assign you any homework about this.
Here we don't mind the frequencies.
What?
We don't mind the frequencies.
Well, yeah, well, I mean, this is the most stupid way of, I mean, If you know edit distance, what would you do? You look this up in your dictionary, it is not there, and you find the closest words in your dictionary, and you offer them. And well, so this is the first thing that comes to mind. But the more important one is the frequencies, right? How many times giraffe happens? Okay, giraffe happens almost 0 times. I have never written the word giraffe in my scientific papers. I don't think so. Okay, so I don't think that if I write this one, I don't think that I meant giraffe, the animal giraffe. Probably if I had written this one, maybe I meant graph, or maybe some other thing, I don't know. Grade, and grade is closer to me, right? Get these two F's off and put them that, maybe grade, something like that. So depends on the context, depends on how many times this word happens, and depends on the surrounding words. And that's what this chapter is about. Okay, we are going to look at. Okay, so non-word spelling errors, any word in that dictionary. Okay, generate all the candidates, shortest weighted edit distance, or noisy channel probability. Okay, we looked at this model, we didn't look at this model, and this is a, again, very nice engineering way of solving stuff. We are going to look at this in a few minutes. Okay, while you are producing those candidates with words with similar pronunciations, okay, for English it is even more important. In Turkish, our usual edit distances are the list of smaller edit distances is your candidates, but in English, if a word starts with this one, okay, probably you should consider this one too. Okay, so pronunciations are these two letters, and this one is the same. So edit distance wise they are very different, but the pronunciations are the same, so the pronunciations become important too. Okay, so noisy channel and classified, and we are going to look at them. Let's look at this noisy channel stuff. So it is, this one was again invented by the in 1950s by the information theory people, communication people maybe. I have the original words. Okay, I need to transfer them through this channel to the other side. These two words come in and they get it out like noisy words. Okay, so they changed. So there are some words in our heads. When we type them on the keyboard, okay, things happen, and the words in my head and the words on the Word document somehow are not the same. So this noisy channel is adding some noise to my words. And they have developed some nice mathematical statistical models to model what's happening inside this channel, and we are going to use them as surprise. The same formula again, noisy channel formula. Okay, it looks like I'm out of time for the second part of the lecture. Let's take a break. Let's be here around 15:31. How many people do I have in the online audience? Just 4 people? Okay. Yeah, if I am logged out, those online people, if I am logged out, don't panic. Okay, I will be back because I need to take this phone with me. Ne zaman geldin? Derste geldiğinde daha vereyim.
Şehirflut. Yani kulut şey, yani yüce şey.
şey bitirdi. Doktora yapmıyor. Nerede çalışıyor dedi?
Ben merkezde
Ha, orada çalışıyor.
merkez bir yere girdim.
Ha, gene buradan çalışıyor ha.
İstanbul'da.
İyi, güzel.
Aileye sordum belki yakın bir şey olursa.
NLP'ci mi? İyi, gayet iyi. Ödev sorsaydın ya.
Tamam ödev sonradan aklıma geldi. Sormak. Fazla vakit kalmıştı.
Nerede oturuyor?
İstanbul'da
Tek mi çıkamıyor musun?
şimdi evlendi de eşi de evlendi.
Hadi evlendi. Vay.
Şeyden evlendi. Şeyde Bursa'da bir yerde mi? Ondan sonra.
İyi be. Sen mi? Ya o şeyler şey, temelinde olan probability, istatistik, bunlar bilmezsin. Yaparsın ama sadece şey, bir ne yazdığı olan olsun çalıştırsın falan.
Abi o zaman çift şeyimiz var.
Onlar da
Yok pardon benim çift sene tek mi ya da benim üstüne bir şey diyecektim. Yani sen şimdi sana bayağı bir kilitlendi ya o. Sen 2 kere gelme.
Tamam. Ben iki
Tamam 2 kere gelme bundan sonra. Ben Cem'le yapayım onu.
olabilir olmaz.
olmadan da bir şey yapabilirsin. Hani engram.
Bir dakika ama bir kere de sen de ben yaptık işte. Şu telefona bakayım.
Yok. Benim ilgili alanım değil yani. Sadece yemek olsun diye yalnız.
Hocam şey ya ben ilk başta gelmemiştim ya sen sonra. Sen hepsine geldin tabii. Cem 2 tane geldi dedi. Cem kalanların hepsine geldi. Sen kalanların 2 tanesine geldin. 3 tane kalıyor.
Eyvallah olabilir. Tamam oldu yani.
Kardeşim benim için sorun yok. Ben şöyle konuştuğumdaki yağları sildim.
Yeni gelen var mı imzalamaya? Yeni gelen imzalamaya.
Yağları sildim. Sonra
Şeyle yaparsan
işte de gerek yok.
So I got only one people left. Melih, are you there or you just forgot to log out? You're okay. Okay, thank you for staying. Um, so let's go back to our what? Say something. I am not in. I was already in. So. Do you see my screen, Meli? Meli, do you see my screen?
Yes, I can see.
Okay, good. So this thing, what is this? Not that one, this one, yeah, okay. Noisy channel says that if I observe a word from, this is my X, and this is original word W, okay? If I observe a word from the outside world, X, what is the probability of this word being W? Okay, measure this probability for me. And if there is such a probability calculation, I can run this calculation for all the words, okay, for all the words, and whichever makes this probability maximum would be my word to choose, okay? So I am sending a word and I am getting another word, is X. Given X, what is the probability of W? Given X, okay, X is fixed, and I am looking at all in my dictionary, all the W's, okay? So that's what I am trying to do here. But the thing is that calculating this probability is kind of difficult, I mean, because if somebody says again RP or LP, okay, so what is the original word? It is ALP or KLLP. So calculating this is difficult. Instead they choose this one. They say that, why don't we write this formula as this, okay? Just invert the probability again using that Bayes formula. Given the word, correct word, probability of writing this word in a wrong way, probability of this word in the dictionary, okay, over the probability of X, okay? Here I don't have to calculate this Px. It is difficult to calculate, and I don't have to calculate this Px. Why? To be able to calculate this W hat, I don't have to calculate this Px. Why? We did this before actually. Maybe we did not. No, maybe we did not. Sorry. But I am asking this anyway. So this Px don't have to be calculated. Well, it has to be calculated to calculate this P value. Yeah, but we are not trying to calculate this P value. We are trying to calculate what? We are trying to calculate this one. So whoever, I mean, this is like a loop, right? I am testing all the W's in my dictionary, one by one. So I am changing this W and testing it and producing all those P's, and I'm going to choose the largest P. While doing this, I am not changing the denominator at all. So this one stays a constant. It doesn't matter for me this one is 0.1 or 0.5, doesn't matter. It is the same for all different types of W's. So I don't have to calculate this. All I have to calculate is this one. I know how to calculate this one. Why? Because I know how to calculate PW. What is the probability of P kalp in Turkish? Just look at the Copara using the maximum likelihood estimation. Calculate it. And then what is the probability of given kalp IC LP? I know this probability, I can calculate it. How? Because I know how frequently people mispressing those K and A letters, okay? I know the probability of people deleting, not including all the letters in a given word, okay? So calculating this easier than calculating this. This one is just a random non-word. What is the probability of seeing this word instead of the real word? This one is difficult. It's like, remember my classical example of the doctors, okay? They say that the patient has cough and high fever, right? And what else? And feel tired. Okay, what is the probability of this patient have meningitis? Okay, instead of calculating this probability, they just invert it and they use this one. Probability of meningitis causing cough. This one is in the medical books. They learn it in the medical school, right? The teachers, the instructors, the professors, they tell them that, okay, if somebody has meningitis, okay, 60% of them has a problem with coughing, okay, and 70% of them has a high fever, 10% of them has tiredness, okay. These one, okay, it's like AN, root and the cause, okay. So this is the meningitis is the main cause. These are the symptoms, okay. Again, this one is the main cause, okay. This is what I see as the observation. So do this, write it this way, and now I'm going to calculate. I know how to calculate this one. Let's look at how to calculate this one, okay. And this will give me the probabilities of words that would explain my observation the best. That's what I'm going to do. So in 1990s, people worked on these, and yeah, we are going to look at this one. So they did, again, classical example from Norway. Okay, somebody typed this word across. There is no such word in English. So probably the typer, whoever typed it, meant something in the dictionary. So words with similar spelling, words with similar pronunciation. Again, in Turkish usually we don't deal with these. Okay, we deal with this. Okay. Usually in Turkish, if I have misspelled a word, it is not because I don't know how to spell the word. It is because I just mistype it. Okay. I didn't see that I am typing it wrong. Okay. So this one usually we don't have a problem with this one because even a 5-year-old kid is a professional speller for us, right? We don't have that kind of problem. So one thing that, again, to calculate the edit distance between two words is using the edit distance, Levenshtein edit distance. Okay, these are the things that we can do: insertion, deletion, substitution. There is another one actually, transposition. And in English, this happens a lot. Instead of typing this one, you type this one. Instead of typing PH, you do this, okay? Because these words are used, these letters are used so much often. In English, this happens. So transposition is the name for this kind of a mistake. So let's look at this one. This is the erroneous word, and these are the candidate correction. Acris. So correct letter. Just I have deleted a letter. To get this error word. So this is what happened, okay? Given acris is the correct word, what is the probability that I type acris? Okay. Or giving crass, these are all words in the dictionary, English dictionary. Giving crass, okay, what is the probability of I am observing a crass again? An insertion, just insert A. and then there is this transposition. Somebody, it looks like somebody just switched orders of A and C. Again, substitution, I wanted to type XS, but I did this, so I'm going to replace CA with an R, etc. So deletion, insertion, transposition, substitution, insertion, and insertion. Okay? So what are the probabilities of each? I know the probabilities of each because I have nice tables built by people who, for example, have access to Microsoft Word, and I have taken 100 people's Word files along with their spelling errors and their correct ones, and I did this kind of analysis. I have seen that in English especially 80% of the errors are within edit distance of 1. We are either forgetting a letter, inserting an extra letter, or deleting a letter, inserting it, or substituting it, one letter with another one, or transpose it. Just change the letters positions, Each one is a cost of 1 or the letter of 1. Almost all errors, 99% of it, within edit distance of 2. Also, don't forget about the insertion of space and the hyphen. While we are dealing with this kind of problems, of course, we are going to use the language models. Unigram, bigram, trigram models, and that will help us a lot, and we are going to see it. So let's look at this Unigram probability. If I am going to make my decision by looking at the Unigram probability, it looks like out of all the candidates, one edit distance candidates, all of the 6 ones, frequency of across and across happened, this one happened a lot. So if your language model is just Unigram, then as soon as you see, what was the original word? Original bad word? Across,
It's across with O.
Yeah.
Change to E.
E.
Instead of the O, it's E.
So as soon as I see this, I listed all the one distance away the words, the words that are only one step away, and I choose this one because this one happened much more than the other words. So but this doesn't pay any attention to the context, right? It doesn't consider about what the meaning of the sentence around myself, etc. So Unigram, we always do that. Unigram is not a very good language model. We can look at the bigrams and trigrams and etc. That's one thing. Language model is going to help us all the time. So let's keep this in mind, but we will come to this one. Let's look at this channel model again. What kind of mistakes I am making, and how frequently I am making them, and can I use that information with the noisy model, So misspelled word, X, it has M number of characters in it, and the correct word is W, and it has N characters in it. And I am going to probability of the edit, What is the probability of original word being this one given this W? What is the probability of seeing this X? And for that one, I have these steps, and maybe if I can get the possibility of these counts, how many times XY is typed as X, how many times X is typed as XY, how many times X is typed as Y, and how many times XY is typed as YX, So we have these kind of tables available for English. So this is sub XY, it is this one. Okay. So X is incorrect, Y is correct. I want to type I, but I typed A. I wanted to type I, but I typed U. Okay? You try to understand why this is happening. I don't know why, but this is the statistics. Okay?
Now, I and you are close on the keyboard to each other.
Well, that's your explanation. Okay? For some people, closer to the keyboard is something explainable, but for the others, it is the way the spelling works in our head. This is the statistics. This is not about the keyboard layout. Of course, keyboard layout plays an important role in forming this statistic, but just the statistics. Okay? So you get this from the data, from the, okay, assume that there is some process running behind the Microsoft Word, and that process is just finding the misspellings and asking you how are you going to change it. After you change it, and you say that, okay, this guy wanted to write I, but he write A, right? So this is just the statistics, okay? We are not trying to explain the keyboard layout. We are not trying to explain how the human brain works, okay? We are not trying to explain the level of touch typing or the just two fingerprinting typing, etc. Just the statistics. So this statistics will give me, I mean, how possible it is that instead of I am writing an A. Okay. So most common mistakes are maybe here. Instead of typing N, I am typing M. M and N very close to each other in the keyboard. Also, usually I confuse them. C and K, maybe C and K. Where is C? C and where is K? K. Well, it is not much. No. Instead of, how about K and C? K. Well, it is not as much as that I thought. No. Substitution between K and C is not that much. So usually I think these are not pronunciation kind of things. But anyway, I'm not going to discuss where this table is coming from. You can get this table statistically.
A and E, probably pronunciation.
A and E, yeah, probably. I don't know. I don't understand A and I don't know. It just happens. And A and I are far away from each other.
Situation.
What?
Words like situation and others you mix them.
What again?
Situation. The word. For instance, AI. And
Yeah, then in transposition. Transposition, but this is about substitution. Transposition is this one. Okay, so in transposition you have two letters involved. So transposition table is what? X, Y, again two-dimensional, yeah. It's a two-dimensional table.
But it will be much larger.
No. Well,
Why not?
well, two-dimensional is two-dimensional, right? I mean,
Yeah,
it's
but-
as large as this one.
Why? Won't we have pairs of letters?
Oh, yeah.
It will be
It will I mean, it's not going to be symmetric, right?
as a
You have two of
so
them.
it will be AB, AC, AD, written as BA.
No, see this one? I have only two letters involved, X and Y. It is not X, Y, Z, T. Okay? So it's going to be, it's going to be A and B. This means that instead of AB, I type BA.
So it will be symmetric.
What?
It will be symmetric.
No, it won't be symmetric. AB means that instead of AB, I type BA. BA is, instead of BA, I type AB. Okay?
Should substitution table be symmetric?
No, because it says that X typed as Y, Y typed as X are different. Instead of X, I typed Y. Instead of Y, I typed X. Those are different. Okay? So, let's go back to this table again. No, this table again. So it is different. So AB is 0, BA is 0. Let's look at this one. So see this one, 13 and 16. It is, yeah, 180 and almost half of it, right? Less than half of it. And M and MN are very different. Okay, again, I don't care, I don't know how this table is formed. I know how this table is formed, but I don't care why. Why this number is high and this number is low. All I know is the statistics. I looked at all the spelling errors and how many times this happened out of million times and etc. So I can get these numbers for each of them. Okay, and then if somebody does this, okay, if somebody say that if I do substitution with A, for example this one, what is the probability of it? If I do transposition with C, if I do deletion with that, so I can get the probability of producing such a misspelled word out of the correct word, okay, given this correctly typed word. Okay, that's what this is about, and these are my probabilities actually. Deletion, okay, how many times these two words happen together, and how many times I did this deletion and insertion and counting and the transposition. Okay, so it looks like for the insertion just inserted, yeah, because you insert a new word. For deletion, you just take one away. You need those counts. For transposition, you need two letters again. Okay, so I have all the probabilities for these letters: deletion, insertion, substitution, and transposition. So that's the channel model, and this is what I get. So if the candidate correction actress, the correct letter T, error letter is, okay, this is just an insertion or deletion if you go from the candidate to the word. This is the probability, and these are all the probabilities. It looks like the highest probability is
Acres.
this one, right?
No.
That's the highest probability.
The lowest, the acres. Oh no. Oh yeah.
Okay.
I'm blind.
3 zeros.
Right. I
It
saw
is
that
it
as
is like
0
at least
or something.
maybe 10 times or
Yeah.
5 times higher than the other. Or yeah, okay. So actress has the highest probability because people keep forgetting pressing the letter T. That's what happens. I cannot show you this in my table because that table was a substitution table. It was not deletion table. Okay. So that's the highest one. So should we make our decision just based on just one word? No, of course we did not look at the context yet. Okay. We did not look at the context yet, and we did not look at it even a very simple language model, which is the Unigram model. We didn't run it, right? Remember with the Unigram, this one talks about P, okay, actress and actress, whatever it is. This one just looks at it. Previously our language model was looking at what is the actress, what is the probability of word actress, right? That was the language model. So maybe we need to put them together. That's what we are going to do in a few minutes. Okay, so that's what it does. So we say here that the probability of given word, given actress, probability of actress is this, but the probability of word is this much, And if I multiply these two, and I'm multiplying with 10 to the power 9 so that the numbers makes more sense, because those probabilities are very, very small, it looks like this is the better alternative than the across. Even though our usual typing behavior says that this is the error you are making. In my Unigram model, okay, maybe I should choose this one because this is the word that happens a lot in English text. Okay, so choose if you are going to list all the words as an alternative to the user, maybe you should put this at the top. And if the difference between this one and this one is too big, it's a very big difference, then without asking the user, you just replace it, autocorrect, because I know that this is going to be a lot larger. Again, this is simple Unigram model. Okay, I'm going to choose that one. If we do the same thing with the bigram model, which is the better one, okay, if somebody typed this as stellar and versatile actress, okay, misspelled word, whose combination of sass and glamour, okay, I mean, if you read the sentence, this is about magazine, right? This is about movies, okay. So if I am going to use the bigram model, given the previous word being versatile, what is the probability of having an actress, and giving the previous word being versatile and the probability of typing across is this one and this one. And if I multiply, what is this? 0.00021. What is that?
Probability actors coming after versatile.
Well, why are they the same probability? That's the probability of this one. What is this? I mean, these are two different things. What is this?
Coincidence.
0.00021.
Coincidence?
No, it's not coincidence. It's different. Remember with the bigram model, okay? You need to multiply. I mean, I am trying to do this versatile across versus versatile across, okay? So I need to multiply the probability of versatile too. So that's the, okay? That's the versatile. So if I do multiplication, it looks like this one is higher, so versatile actress. So even though my Unigram model chooses this one across because it happens a lot, across versatile across doesn't happen much. So bigram model says that choose this one, okay, across, which is the correct one for this sentence, of course. Okay, for this sentence. If you are going to do the spelling error check, spelling correction, based on just one word only, this is the correct solution across. But if you are going to look at the context, of course it makes a difference what you have as your previous word. And if you are going to do this with a trigram model, okay, then you have to include all these words inside it. Good. So this is how you make a decision, by just paying attention to what kind of letter mistakes we are making while typing the words. Also, how we combine our language model inside the spelling correction. I remember I kept saying we can use our language models in the real world application, and this is a real world application. Now we are using our language model in this real world application. Remember the validation of the results, either calculate the perplexity, which is an intrinsic evaluation. But if I am using my language model to correct my spelling errors, okay, to correct my spelling errors, then in that case, this is how you use your language model. Okay, and the result of this spelling can be measured very conveniently. You say this language model, unigram or bigram or trigram language model, produces 60 correct results out of 100, okay, and the unigram model produces only 50, so this one is better than the other one. You can say that. Good. Okay. So we have chosen this one. Evaluation again, just get some. Wikipedia has a common list of English misspellings, or Peter Norvig has them. And I think I found it yesterday. Yeah. Let's look at this. Peter Norvig's. Did I type it before? Okay. Peter Norvig's. Yeah. Spelling word set. Let me see if I can find it. Norvig. Spelling corrector. Data set. Yeah. Engrams, and yeah, here it is. Count one. Counts for all single edit spelling correction edits. Okay, and spelling errors. Half a megabyte. Corrected from Wikipedia. See, all the misspelled words from Wikipedia, and I have how many lines? How do you measure the number of lines in?
WC-L.
It doesn't work here. Okay, so there are very many of them, but some of them, as you see, for walking, for some reason somebody typed weak. How about this one? Walking. Oh, this is good. Yeah, waking, walking. So just because of the fast typing, it happened that way. So go back to the slide for evaluation. Okay, okay. Of course, you are not going to evaluate it using by just these words only, right? Because this one ignores the context, right? This one just ignores the context. But to get those tables, remember those tables? These are how those tables are formed, right? Instead of surplus, people are typing these. So you can get the statistics for, instead of S, people type C. Instead of this, people type this and that. And that's where you get those tables. And with the tables, with these tables, it is possible to calculate these kind of probabilities. Given the word, what is the probability that I am mistyping it this way? The other way of doing things, given the misspelled word, what is the probability of having this correct word, is not that easy to calculate, just like the doctor's example. Okay, good. So noisy channel. Okay, let's look at some other interesting problem. This happens a lot. Okay, leaving in about 15 minutes to go to her house. Of course, this is a correctly spelled English word, but it is not the correct word. Instead of saying minutes, I am saying minutes. And the design a construction, instead of I am saying an. Can they leave another English word which is spelled correctly but the word is wrong? Okay, conducted mainly by, no, B. Instead of by, I type just B. Okay, so the bad news is that 25 to 40% of the spelling errors are real words, and usually in Turkish this number is usually bad, worse, because when you mistype a word, you usually type them wrong when you are typing the suffixes, because when you say olduğu, olmadığı, olduğundan, etc. If you just omit one of the syllables there, then your word will spell fine. Olduğunu, olduğundan, olduğuna. Just if you type the last letter wrong, then your word is fine. It will be a nicely spelled word, but the not correct word, incorrect word, etc. So real word spelling error is bad. So what are we going to do? Okay. For each word in the sentence, generate a candidate set. I know that all the words in my sentence are correctly spelled, but one of them or some of them may not be correctly spelled, may not be correctly written there. So for each word in the sentence, generate candidate set. Don't forget to put the word itself in it too, okay? So word itself might be the correct word too. All single letter edits that are English words, words that are homophones, that is the
homophone.
well, we talked about it. It's the
I know what a homophone is, but how to get the set of homophones?
how do you get a set of homophones? Do you have an idea? Anybody?
Somebody.
You go to Webster. Okay, let me see.
Try to produce homophones.
This one. Accurist. No, just get a real letter. I'm trying to go to. Okay, good. I'm trying to go to Webster's site. Okay, good. Is it a word? Just tell me a word, actress.
Open a Webster's.
Okay. So Webster dictionary, good. You go there, okay. All the dictionaries have English dictionaries. These kind of entries in them, just next to them, okay. This is how you pronounce the word. Okay. So if you change this letter to something else, your pronunciation changes, right? So instead of making those changes here, letter by letter, you do the same thing with the pronunciation version of the same thing. So you get all the homophones. So it is more difficult than Turkish, yeah. Okay? It is more difficult than Turkish. So go back there. I get all the homophones, all of them, and the word itself, and choose the best candidate. Either a noisy channel model, okay. With the noisy channel model, you say that what is the edit distance between these two with the noisy channel model. So, and the interesting is that the input and the output would be the same thing. So, I mean, it's an interesting question for the noisy channel. If I type the, what is the possibility of the original word being the? Is it 1.0?
No.
Why not?
Maybe somebody tried to write he.
Yeah. But I mean, so you cannot say this is 1.0. You have to assign some kind of a probability. Noisy channel has some answer to it, and we will look at it in a few minutes. I don't have much time, but okay. So for each word, let's say this is my sentence. In my sentence, these are not the letters. I have n words. For each word, I have produced these candidates, and for each word, the word itself inside the candidate list. Okay. For the word 1, word 1 prime, word 1 double prime, 3 prime, etc. For all of them. And then I do this. For example, 2 of the, okay, all of them are spelled right, but for 2, maybe I meant 2, maybe I meant 2, etc. So 4 candidates. Of could be this one, or this one. Q could be this one, and this one. So my task is to find a path in this graph like that, okay? So start and end. Find a path in this one. And this path will consist of observation is 2, the probability of really the word being 2. Observation is off. I mean, what is the probability of off, and 2 and probability of the. Okay? All the words in this graph spelled correctly. There is no misspellings in this graph. Okay? So that's what I do. It's going to be expensive. What is the cost of checking all these stuff? 4 times 3 times 4. So if your sentence is 10 words long, then it's going to be, if on the average it's like 3, it's 3 to the power 10. It's a lot of numbers, right? It's a lot of numbers. That's not good. So some approximations. Okay, some people say that. Why don't we use the simplification? Okay. Each sentence should have at most one incorrectly written word. So I am going to test it. It is either 2 of the, like etc. So you cannot have more than one misspelled word in the sentence. That will be a simplification that will make things a lot easier. Okay. So where do we get the probabilities again? For the typing mistakes, we had the channel model. For the language model, we have our unigram, bigram, trigram, etc. Models. Do I have? Well, I have some more slides, but I am out of time, and I think I will stop here, and I will finish up I will finish up this chapter next week. Then I will start talking about part of speech tagging. We will try to mark each word in a given sentence with their parts. For example, this one is an adjective, this one is a verb, this one is a noun, this one is a preposition, etc. Okay, and that will be another classical NLP problem. Okay, that's it for this week, and let's thank our online. Oh, okay, we have one more people, Yusuf and Melih. Okay, see you guys next week.
Have to wait for the
Şey,